Well, greetings everybody. Here is an example that is from the assignment on my math lab, and I've got it all worked out, ready to go. But I think it'd be best to show you something a little simpler first that captures what's happening over here, but in a way that's maybe a little bit easier to see. So here it is. Let's talk about the difference between these two functions. Okay, there is very little difference between this function and this function. Okay. But there is one very key difference, okay? If I were to graph this function, it would be a line like so, and there would be a hole in the graph at the point 2 for x, 5 for y. So that point would be left off, but all the other points around it would be there, okay? The reason why this point must be left off this graph is because it's undefined at 2. When you try to plug in 2 for x in this function, you don't get an answer. It's undefined. So there can't be a point where the x is 2. Now, as far as why it looks like this otherwise, why it's a line like this, and why besides that hole it looks just like this other one, I'll explain in a minute. Okay, so that's this one. It's a line like so. There's that hole in it right there where that point is not included. This one, on the other hand, is a line exactly like this one. This function's graph is just like this one. Everything identical, except for instead of having a hole right there at 2 and 5, that point at 2 for x, 5 for y is included. Because, in fact, for this function, when you plug in 2 for x, you get 2 plus 3, which is 5 for y. So that's why that point's got to be there. So even though these might look a lot different, the graphs are hardly different at all, but this one does have a hole and that one doesn't. And let's talk about why that is. So notice that this function can be reduced to that one just by canceling the x minus 2's, okay? So if you saw that first function as x minus 2 times x plus 3 over x minus 2, and you canceled those, it would reduce to x minus 3. But we'd have to have this condition that it only reduces to this if x is not equal to 2. The reason for that is if the x was 2 right here, when you cancel this x minus 2 over itself, that x at the end of the day is a number. And if it was 2, you're canceling 0 over 0. So you can't actually do that canceling and reduce it to this in that case. In all other cases, they're the same. Okay? So this function, f of x, is the same in every way as g of x is, except this function is undefined at 2, but g of x is defined to be 5 at 2. Okay? That's why their graphs look identical, except for this one having a hole where the x would be 2 and this one not. Okay? They're identical because this one reduces to that one with only one exception, in the case where x was 2. Okay, so that's called a removable discontinuity. Like we would say this function is not continuous at 2, but it's just missing that one point. Otherwise, its graph is cohesive in one piece, just missing one point. All right, now that's what's happening over here with this one. So this function that I'm given, it's undefined as it is at 9. And it says, okay, say we overlook that. Can you define f of 9 in a way so that it is continuous at 9? Okay, so it's kind of like this one. It's this function that has a graph and there's just one point missing. There's just a hole in it somewhere, and if we could fill that point in, if we could plug that hole, then it would be continuous. Okay, it's kind of like that. So it's like if only this point were there, this function would be like that one, exactly like it, and it would be continuous. Okay, all right, so let's study it like this. Let's say maybe this, kind of like in my first example, would reduce to something else a little simpler that is defined at 9, and whatever that simpler form gives me is what this original needs to be. Okay? Same thing. That is perfectly analogous to figuring out where that point is and plugging the hole, and then it becomes continuous. Okay? All right, so let's do this. So to reduce this to something simpler, I need to know some factoring forms. To factor that top part, it's the difference of two cubes, and for the bottom part, it's the difference of two squares. But I can factor it, and then I can do some canceling, and it reduces to this. Now, This is the same thing as that in every way, except for at 9. This one's undefined at 9, but this one gives me 27 over 2 if you put 9 in. So if this one only gave me 27 over 2, then it would be continuous. It's a graph of some kind that has a hole in it where s is equal to 9. But if it was there, and if that point was 9 for x, 27 over 2 for y, then it would be filled in. There wouldn't be a hole in the graph, and it would be continuous in that case. So that's why this answer then is that, all right, this function is not continuous as it is. It simply isn't. But if when you plugged in 9, you got 27 over 2 out as an answer, then it would be continuous. The graph would be complete. The point that had a hole in it would now be included, and you'd have one solid graph.